I am drawing a set of planes, and I am now indicating the atoms by certain number. So here I have written 1. I have marked, that is, suppose atom number 1. Then I have written atom 2, and at an angle I have written atom 3. Okay, between 1 and 2 the distance I have written is A0, and between 2 and 3 I have written a distance D0. So along the angular direction, 0, this is atom 0, 0, 2, 3, the angle is D0. Whereas between 1 and 2, horizontal direction, the spacing, atom spacing is A0. So my first question is, why the atoms are arranged in this fashion? Why the spacing between 1 and 2 is A0 and not any other value? This is my question to you.
Because they are in equilibrium.
Right, equilibrium with respect to what?
With respect to
Minimum energy, sir.
Minimum binding energy, right?
Yes.
Right.
Yes.
Yes, they have a their potential energy state is minimum. Okay, because whenever we consider two atoms, and if we draw a plot, we consider, say, one atom at an origin and another atom at a certain distance, say A0, we have to answer why is that? Why that particular distance is maintained for that particular metal? For every metal, we know the atom spacing is different. Lattice parameter is different, which is their identification mark. So what happens is, between the two atoms there is a repulsion, right? There is a repulsive force, and repulsive force or repulsive energy, here you are plotting, say, energy, potential energy phi, and here I am suppose plotting distance x along x-axis. Along y-axis I am plotting energy phi. So there is a repulsive energy, and there is also an attraction energy. There is a repulsion and there is an attraction. So attraction is negative and repulsion is considered in the positive direction. And both of these decreases with the increasing distance between the two atoms. Suppose my first atom is 0 and second atom is 1. So what we have to consider is the net energy. What is the resultant? When we consider attraction energy and repulsion energy, there is a resultant. And how the resultant goes? Resultant looks like something like this. So this is the resultant R. This is my resultant R. So that decides what will happen between these two atoms. And why they are at a distance of a naught? Because at that position the potential energy is minimum. A naught, the potential energy is minimum. We write it as phi naught. Phi naught. If I shift this atom a little bit, suppose I write that shift as displacement u. So if I give a small shift, displacement u, what will happen to the potential energy? Potential energy will now increase from this particular value phi naught to a higher value. Say I represent that higher value as phi u, the potential energy at a displacement u. Can you understand what I am saying so far?
Yes, sir.
Yes,
Yeah.
sir. Yes,
So,
sir.
yes. So the potential energy will increase if you stretch them, or the same thing will also happen if you compress them. And we consider, basically the curve nature is such that it's more or less very symmetric. If we look into this minima, it's actually very symmetric. So in general, whether you stretch or whether you squeeze by compression, the typical change in potential energy for a particular value of displacement is more or less similar, not very different. Typically the values that we get in metallic systems. Now, don't think that this phenomena is only taking place between the atom 1 and 2. Here I am drawing 1 and 2. So is this phenomena taking place only between 1 and 2? This is my question.
Sir, every atom will be interacting with each other.
Yes. That is what my point is. So if I consider 2 and 3, suppose if I draw atom 2 and at an angle atom 3, so here I am drawing atom 2 and here I am drawing atom 3. The same phenomena is also working between them. I'm drawing it at an angle so that you get resemblance with this schematic. Same concept is working.
Sir, your voice is breaking.
Sir, your
If
voice
you
is
draw
breaking.
the distance curve, so
Excuse me,
this.
sir. Hello.
Okay.
Hello,
Yes.
sir. Sir, your voice is breaking.
Hello. Yeah. Any better now?
Yes, sir.
Yes, sir.
Huh? Better?
Yes,
Yes. Actually, I'm coming 1 minute. Yes, sorry. Connectivity problem actually. Am I audible now?
Yes, sir.
Yes, yes. So between 2 and 3, same phenomena is taking place, and there will be another minimum energy value which we can call, say, phi naught dashed. Okay, because their equilibrium distance of separation is different, and that's why they are separated by a different distance d naught. So basically this is the story, and by this interaction all the atoms are arranged in space inside a solid. Now let me come to my next slide, which will be a bit complicated, but don't get panicked. I will explain everything.
Sir, in particular, this potential term which we are using, it is
Yes,
referring
yes.
to which which potential?
Ultimately, it's the potential. Ultimately, see, there is a binding energy, right? Binding energy. So between two atoms, there is a net, there is an attraction. Between two atoms, there is a repulsion. So in total, they will situate at a position where these two are perfectly balancing each other. So at that position, what is the potential energy between them? That is dictating their spacing. If I'm not very clear, then you please also have a look, and you may also add. I may not be completely convincing every time, because
Sir,
some, yes, yes,
I was asking in the sense that
yeah,
in many times potential energy, like strain energy, in one sense can be referred to as potential, because when if a material is strained, then
right, right.
deformation is in the atomistic level. The
Yes, yes. So here also we are considering its distance, right? If you change their distance, then am I audible?
Yes, sir.
Yes, yes, sir.
Yes,
Yes,
yes.
sir.
If you change their distance, if you change their separation, distance of separation, the energy will change, the energy will increase. And as a result, they will again come back to their equilibrium spacing, A naught. So here, what we are trying to explain is 1 and 2. Say I am now in this particular schematic. 1 and 2 is connected by a spring. 1 and 3 is also connected by a spring. Okay, 1 and 2 is connected by a spring. 1 and 3 is also connected by a spring. So here in this, if you can see the marking that I am making, I am showing the story what will happen between atom 1 and 2 if you stretch them like this. If you see the blue arrows I am drawing there, I am stretching the structure like this. So if I stretch the structure like this, atoms like this, what will happen between 1 and 2? Can you tell me? This is my question.
The bonds are also stretching, sir.
The bonds are stretching, right? So there is a spring. So that is what I am trying to show in this plot. If you see the marking that I am making, so if you give a stretching U and if you release the load, then what will happen? if you release the load?
Atomic vibration get started.
No. The answer is
Contract.
it will go back to its initial position. If you give a stretch of small amount of U and release, it will go back. Okay, its energy has increased from here to a particular value, and if you release, it will again go back to its equilibrium position. So that we call as elastic displacement. Elastic displacement. But if you can see these shaded dots I have written, what it's trying to show is if you stretch them too much, if you stretch them beyond a particular point, if you stretch them beyond a particular point, then what will happen? Then
Breaks.
They will
spring breaks. That is I am trying to show. That I have written break. There the spring will now break. So that breaking is basically fracture. So atomistic theory, if you consider, the principle always remains the same, that what will happen is as you are stretching, the energy is increasing, and when it reaches a peak particular criticality, suppose it reaches a activation barrier, you can see the activation barrier. Let me draw in a different color. I am drawing the activation barrier. So it's something like this. What will happen? That if you exceed a limit, then automatically the atoms will separate. And when the atoms will separate, what will be the energy between these two atoms? Again, it will come to the minimum because there will not be any interaction now. So their binding energy will fall. Their binding energy will fall. So my point is, if you have to break them, you have to exceed a activation barrier, a maximum peak energy point, and then it will come down once again because they will break. Similar story I am trying to show in this picture. If you see the mark that I am making here, I am trying to show the story between atoms 1 and 3. Here I am trying to show what is happening between inclined atom planes, these atom planes. So I am drawing two atom planes on which what kind of stress is acting?
shear stress.
Shear, right? Shear. So here the possibility can be they shear with respect to each other. They have a shear movement with respect to each other and they move like this. So this possibility comes between 1 and 3 layers, these layers. And this possibility doesn't exist on this particular plane if you stretch them, or perpendicular planes, they cannot shear. So when you consider shear, here I am drawing the same story of 1 and 3. If you see this plot, this is 1, this is 3. What is happening is 1 and 3. Why 1 is there at the position of 1? Because there it's the minimum binding energy. Why 3 is there at its position? Because 1 and 3 there is a minimum binding energy position. Then why the next atom is here? Because 3 and next atom, say 4, is having this kind of a barrier. Then why the next atom 5 is here? because 4 and 5, they are following same kind of a behavior. So overall, now if I consider what I have to do to shift atom 1 to 3, what is your answer? If I have to slide, suppose I slide one plane with respect to the bottom plane. That means atom 1 is moving into the position of atom 3. Atom 3 is moving into the position of atom 4. Atom 4 is moving into the position of atom 5. To do this, what I have to do?
You need to cross the activation barrier.
An energy.
Absolutely. And what is the activation barrier? You please have a look between 1 and 3. I am drawing. Isn't it? This is making the activation barrier. If you follow, if you can cross atom 1, an activation barrier, this maximum location, some point here, then again the energy will fall. If you move 3 and cross some location, then again it will fall. Again it will fall. So if you can do this, if you can provide sufficient energy to cross that barrier, then you can slide. Then you can do plastic deformation. Similarly, if you can cross this barrier, then you can cause fracture between 1 and 2. So wherever plastic deformation theory you consider, wherever fracture theory you consider, both derivations, you have to cross an activation barrier. So that barrier I am showing in this picture. This is kind of a barrier. So every 2 atom, if they have to slip, if this atom has to move to the next position, it has to cross a barrier to here, it has to go here, so it has to cross the barrier here, like that. Okay, so this concept you please have. We need this concept for some other explanation, which I will come to a little time after. Let us see the same plot again. Repulsion R, attraction A, net resultant I write resultant. This is phi. This is phi naught, minimum position. These 2 atoms are separated by a distance lattice parameter, say A naught. I am considering only elastic problem here. Only elastic problem. Okay. What I have done? I have given a stretch. I have given a stretch. And because of that stretch, this atom, suppose this atom I name as 1, this atom I name as 2. Atom number 2 is now in a new position, which I write as 2 dashed. 2 has moved to a new position 2 dashed. And what is the amount of displacement happened? U. Displacement is U. When the atom 2 was at its equilibrium position, what was the displacement? U equal to 0. At that position, what was the energy? Minimum. Phi naught is the minimum. Now, when you are bringing to 2 dashed, energy is increasing to a new value phi, which is a function of U. So you can see ultimately this energy is a function of displacement, distance or displacement. So here I am therefore writing in a more simple way that phi equal to phi naught plus a function of u. Okay, and the way this potential energy distance plot works between the atoms, this function is called, it has a nature which is it's called continuous and analytic function. Continuous means phi is moving continuously with displacement or distance. It is not discontinuous. If it is discontinuous at any point, you cannot do derivative. And analytic means that it has a derivative at all the points. So continuous and analytic function of u. Phi is a continuous and analytic function of u. And if that follows, as that follows, the change in phi can be represented by this expression that I have written here. What is this expression? Am I audible?
Carrier expansion.
Yes.
Yes.
Yes. Yes. What is this expansion? Expression? Taylor series, right? Taylor series. And Taylor series actually obeys because phi is a continuous and analytic function of u. So I am just writing the Taylor series expression to know what is the new energy state, that is phi u, and how that is related to phi naught. So here I am writing phi u equal to phi naught plus d phi by du at u equal to 0. What is d phi by du?
First order derivative.
What is that? Phi
It is
u
zero, sir.
curve? Phi u curve? Slope, right? Slope.
Right, zero, sir.
D phi by du, d phi by du is the slope, right? Very good. This is slope, slope of the curve. Very good. Then 1 by factorial 2, d2 phi by du2, again at this point, u equal to 0, u equal to 0 into u square plus 1 by factorial 3, d3 phi by du3, again at that particular point, u equal to 0, u cube, plus the series goes on. The series now goes on.
So can you explain this graph once again, the left one?
This graph that I am drawing, I am marking, this
Yes,
one.
sir. Yes, sir.
Yes. Actually, as I said, that between two atoms, there is one atom here, there is one atom here. So I am trying to explain why these two atoms are a particular spacing. That's what I have explained from the very beginning, that why two atoms follow a spacing, a naught. You answer, you tell.
Because there is minimum energy.
Because there is minimum energy. And what is that energy? That energy varies with their distance. That is a combination of attractive energy and repulsive energy. So I am drawing the energy curve again. I am drawing the energy curve once again. This is the energy curve. Okay, this is the energy curve. What happened? Could you follow?
Yes, sir.
So if I move, now I am applying a tensile stretching. Whether I apply a tension or a compression, as I said, it's more or less the thing is the same. So if I give a stretch, suppose I consider this atom to be hinged at this position. It's not moving. Suppose this part is hinged. So only movement I am trying to show by this atom number 2. So atom number 2 is displacing by an amount of u. And if it displaces by an amount to u, what will happen? Its energy will now increase or decrease?
Increase.
Increasing to here. And how much it increased? That I am trying to explain. The new energy is phi u. The energy has increased to this point, which I said is energy has increased to this point. So corresponding energy is phi u. So how phi u can be represented with respect to u? If I know the value of u has a value. Okay. And phi is a function. What kind of function you know? You know function, polynomial function. Say phi equal to constant a plus bu plus cu square, something like this. Cu square plus du cube, depending on the nature of that curve. Okay. Phi naught as a constant value because it's the starting position. You know the binding energy between the two atoms in a particular metal. So phi u can be represented by a Taylor series expansion. That is what I am simply telling. Phi u equal to phi naught plus d phi by du at u equal to 0. That means what I am saying is you do a derivative, you do a single derivative of phi with respect to u, and at the place of u, you put 0, 0, 0. You will get a value. Right?
Yes, yes.
Then 1 by factorial to d2 phi, you do double derivative of this expression. And at the position of u, you put 0. Again, this will get a constant value. So these are the constants. That's what I am trying to show. These are the constants. And this is u. U is variable. Then 1 by factorial 3, d3 phi by du3. Again at u equal to 0. You do 3 times derivative, put u equal to 0. You will get this constant. And then u cube plus some other constant into u to the power 4. And this series goes on.
So they are the coefficients of the
Yes. Coefficient, basically coefficient.
Sir,
Yes.
sir, I have a doubt.
Yes.
Sir, if we already know what is a function of phi, then why
Yes.
do we need to calculate a Taylor expansion? Because we can just we could put our u and then we will already get phi.
Now we will understand why we are doing this expression. You know phi, but it also varies because in different material these values are different. This function is also different. It's also material specific. So it's not that easy. These values, these coefficient values are also different depending on the different material. Okay, so
Sir,
I am
but if
just-
we calculate, say d5 upon du or d2 phi upon du square, then we should
Yes.
we should know what is phi. That is what I'm trying to say. Because if we know
Yeah.
what is phi, then we could calculate what at
Yes,
what
yes.
point we need our u.
Yeah. So anyway,
Sir,
just hang
what-
on. Huh? We may be able to answer at a later stage. But what I am trying to show is this. What I am trying to show is this. Can you tell me what is the value of this particular term?
Zero.
So 0, sir.
Why it is 0?
So d5
Because the
upon
slope
du
is
will be 0.
Why?
Because that is the
Slope is 0,
minimum.
sir. Minima
Why?
because
Because it is minima. So at the minimum point, slope is 0, right? At the minimum point, slope is 0. Okay. So what I am doing, I am erasing that term. I am erasing that term. Okay. Now comes the importance of the exact value of u. U can be small or U can be large, right? Ultimately, here I am considering continuous. Why I am considering continuous?
Because we can
Yes,
get the derivative.
that means if it fractures, that logic will not work anymore. Okay, then it will become discontinuous. It will truncate it. The function will truncate if it breaks. That's why I am applying this approach until and unless phi remains a continuous function of u. And how long that obeys? Till its elasticity is valid. That's why this expression is applicable till the elasticity is valid. That's why I am applying Taylor series in the elastic domain. Now, in majority of the metal that we work on or ceramic that we work on, whatever you say, what is the typical value of U that we encounter? What is the typical displacement, elastic displacement that we encounter? The answer I am looking for is high, low, very low.
Very low.
Very low. Okay. So don't be don't take anything as granted. It depends on ultimately for the material system what level of U actually is for that particular material. If the U till elasticity obeyed is very, very small, then what I will do? If U is very, very small, then what can you say? Then
Can be neglected.
Yeah, U3 to higher order terms, whether you neglect or not, that is a different issue.
It will not matter.
It will not matter. You are not neglecting. The material is deciding what is the elastic strain it can take. If the real value of U is very small, then what will matter to you, as the student has rightly mentioned, that this first term will have some meaning to you. So don't always take a value very, I assume. It is no assume. We are not assuming anything. Its material is deciding what is the value of u. It's not me and you. And accordingly, it is deciding this term will work, this plus this term will work, this plus this term will work, or other terms will also come into play. Okay. So now my thinking is only, let us concentrate on the first two terms. Phi u equal to phi naught plus 1 by factorial 2 d2 phi by du2 at u equal to 0 into u square. Okay? Now what you do, take phi naught on the other side. So I shift my equal to here. I erase the equal to there. And I put a minus sign there. So what this term basically tells is how much is the energy change has taken place because of the displacement of u. So phi u minus phi naught is the net energy change. Is it okay?
Yes, sir.
To give that energy change, inside the material, there has been an energy change. Now, why that energy has changed? This is my question to you. Why the energy has changed?
Because the arrangement has changed.
No, because you have applied a force, isn't it? Otherwise, it would not have changed, isn't it? Because you have applied a force, a stress, right? You have applied a force, say I write as F, and that is why basically you are providing this energy in the form of a force. Okay, so how to get the value of force? I'm erasing this part. How to get the value, how to get force, the expression of force? How to get the expression of force? What is force?
F equal to
minus du dx.
Yes, yes, very right. That force, energy is force into displacement. So force is change in energy per unit displacement. इसको डेरिवेटिव कर दो with respect to du, and that is your forceps. That is your forceps. So इसको भी डेरिवेटिव करना पड़ेगा अभी. With respect to du. Right? Is it clear?
Yes, sir.
So what would be the answer that you will now get? Here 1 by factorial 2, that means half. This is a constant, and derivative of u square will be 2u, right? So answer will be F equal to ठीक है, F equal to d2 phi by du2 at u equal to 0. What is d2 phi by du2 at u equal to 0?
Positive.
What is this term?
A constant.
Right, constant and curvature, right? If d phi by du is the slope, d2 phi by du2 is the curvature, right? So curvature of this curve with respect at this point. So what is the beautiful expression we have come to? So what is the expression? Now you tell its name. You now name the expression. We have come down to a very important expression. What is the name of this expression? What is the name of this expression? Am I audible?
Yes, sir.
Yes, yes. Now you tell. Who said yes, sir? बोलो, ये एक्सप्रेशन क्या है? एक बार बताओ, क्या F क्या है बताओ? What is F? Force. What is
Force and
U?
energy.
What is U? एनर्जी मैं बोला, मैं तुमको बोला क्या? F क्या है बताओ? बोलो क्या है F?
F force है sir. U displacement.
फोर्स है, F फोर्स है. U क्या है बताओ? U क्या है बताओ?
Displacement.
डिस्प्लेसमेंट है. और ये टर्म क्या है बताओ? ये टर्म क्या है बताओ? ये टर्म क्या है बताओ?
कांस्टेंट है सर.
कांस्टेंट है. फिर तुम बताओ क्या हुआ?
Hooke's law है
फोर्स
सर.
इक्वल्स टू हुक्स लॉ हो गया ना?
Hooke's law, sir.
Hooke's law. So that answer I was looking for. ये क्या difficult question था? Hooke's law. So basically we have derived the Hooke's law. Basically we have derived the Hooke's law. Okay. Force equals to some constant into displacement. What is this constant? What is this constant?
Young's.
Young's modulus, right? So what is the definition of that constant? If someone asks you, now you will be able to tell what is the definition of that constant. It's basically the second derivative of binding energy with respect to displacement and the curvature of the minimum point of the potential versus distance curve between the atoms of a particular material. So as I said, for different material, the nature of this potential displacement curve or the level is different. Funda is the same, but whether what is the value of phi u level is different, and the expression may also be a little different. So for different metal, you have different values of this term. So you have different values for this term. And what is even more important, Y or G is a very important constants. What are these constants called? What are these constants called?
Young's modulus and shear modulus.
Young's modulus, shear modulus. You are very right. But they are also have another name. They have a very bigger role. And there is a difference between material yield strength and material's elastic modulus. You know that yield strength and elastic modulus are not the same. What is the difference? Who can tell? What is the difference between?
So
You know what is yield strength?
Strength at 0.2%.
What is the yield strength and what is Young's modulus, Y, or G? There is a fundamental difference between them. What is that difference?
So yield strength is the strength at 0.2% strain.
ठीक है, वो तो समझ गया, वो तो बच्चा स्कूल का भी पढ़ाता है क्लास 12 में, है ना?
Sir, yield strength is
इनका एक फंडामेंटल डिफरेंस है. क्या फंडामेंटल डिफरेंस, मैं ये जानना चाहता हूँ. फंडामेंटल डिफरेंस. Who can tell?
Yield stress is due to normal stresses and shear stress is due to.
वो तो हो गया. यंग्स मॉडुलस भी नॉर्मल शेयर, यंग्स नॉर्मल और जी शेयर मॉडुलस.
सर एक परमानेंट डिफॉर्मेशन के लिए
वो तो पता है, वो तो बच्चा भी बोल देगा कि ये इलास्टिक डिफॉर्मेशन, वो प्लास्टिक डिफॉर्मेशन, वो बोल देगा. अच्छा आंसर बताओ, फंडा देके बताओ.
सर यील्ड स्ट्रेंथ हम लोगों का स्ट्रेस जो अप्लाई करेंगे उसके ऊपर डिपेंड करेगा.
ना स्ट्रेस अप्लाई के ऊपर तो करेगा ही बाबा.
और जबकि
यील्ड स्ट्रेंथ खुद ही तो एक स्ट्रेस है, वो तो स्ट्रेस के ऊपर कैसे डिपेंड करेगा? वो तो एक पर्टिकुलर वैल्यू है.
मतलब
हाँ तुम ठीक बोल रहे हो, बोलो. स्ट्रेस के वो तो खुद ही स्ट्रेस है.
हाँ सर. और जबकि बाकी दोनों जो लिखे हैं वो मटेरियल प्रॉपर्टी है, वो एक
वेरी गुड. क्या तुम्हारा नाम बोलो?
आदर्श मिश्रा.
आदर्श मिश्रा, बहुत बढ़िया आंसर दिया तुमने, बहुत अच्छा बोल दिया. ये आंसर है. ये इसको बोलते हैं मटेरियल्स प्रॉपर्टी, क्योंकि ये इजीली चेंज होता नहीं है. मटेरियल्स प्रॉपर्टी जैसा हम लोग का डीएनए है वैसा टाइप का है. कि तुम जो भी करो, कोई पढ़ाई करे ना करे, डीएनए में कुछ चेंज होगा नहीं. लेकिन यील्ड स्ट्रेस ऐसा चीज है कि तुम उसको लेकर अच्छा से पिटा, अच्छा से उसको हीट ट्रीटमेंट किया, उसमें कुछ कार्बन डाल दिया, उसमें कुछ एलॉय कर दिया, यील्ड स्ट्रेंथ तुम बढ़ा सकता है. Am I clear?
Yes,
For example, you are working with iron. You are working with iron. It has a Young's modulus of 210 GPa, suppose. Shear modulus of 80 GPa. How can I tell? How can I tell? Steel, steel. In general, some steel you make, what will be the Young's modulus? Why? What will be the shear modulus of steel? कोई तुमको पूछा कि एक स्टील बनाया कितना टिपिकल यंग्स मॉडुलस होगा, शेयर मॉडुलस होगा? क्या आंसर है? क्या आंसर दोगे? व्हाट विल बी योर आंसर? हाँ, मतलब very very close. That's why material property, because even if some carbon going into interstitial position, basically the iron-iron bond is not changing significantly, because how much carbon you can put, majority of the bonds will, there may be a little stretch, there may be a little change in, very little change, ignorable change in lattice parameter. That's why whether you consider iron, whether you consider steel, Young's modulus 210 GPa, shear modulus 80 GPa, Poisson's ratio 0.33. If you do this, take these values, nobody can challenge you. But if I ask you what is the yield strength of steel, what will be your answer?
That may be very high.
Huh?
Heat treatments that we can vary.
That how much? From what to what? Steel generally strength varies, yield strength varies from what level? You tell. Very soft steel, there can be IF steel 200 MPa strength, yield strength, and the steel that Sir Hari Badesia has made, its yield strength is 2 GPa. Now people are even making higher and higher steel. If you add more carbon, yield strength increases. If you do annealing, you will get a low yield strength. If you do water quenching, you will get a high yield strength, right? So that means this is not a fixed material property. It's dependent on geometry. It's dependent on alloying. It's dependent on processing. If you do casting, it will be one value. If you do rolling, it will increase. If you do annealing, it will again decrease. But Young's modulus, fixed material property. Why it is fixed? Because it's a function of bond energy. And bond energy is something that is fixed for a particular material. So stress and strain, basically what is stress? Force by some kind of area we divide the force, whether it's an initial area or it's a instantaneous area. It can be initial area. If I divide by initial area, what is this stress called? Initial cross-sectional area, what is this stress called?
True engineering.
Engineering. If I divide by instantaneous, then it's called what? True stress. Please read these things. In this course, everything cannot be covered. But one very important thing we realized, that the initial part follows a straight line relation. Here also you can divide it by original length, or you can divide it by instantaneous length, whatever you can do. Ultimately, this relationship will hold even if true or engineering, whatever concept you consider. The line will be straight, and the slope of that line will decide your modulus, average modulus. If you unload, what will happen to this curve? It will go back like this. Now my next question. Suppose I ask you a stress strain curve of rubber. What is how the stress strain curve of rubber looks like? How the stress strain curve of rubber looks like?
Its elastic modulus changes with deformation.
Something like this. If you go, it will go. If you unload, what will happen? It will come back to zero ideally. If it is perfectly elastic, elastomer. If it is perfectly elastic, it will come back. So why a metal is following a straight line relationship, whether rubber is going all over the place with its curve and coming back to the origin? Why the difference is? This is my question.
So it's a polymer. So there will be sliding.
देखो वो सब छोड़ो, बेसिक अभी जो मैं
स्लो फॉलो नहीं करता.
नहीं, मैं वो नहीं बोलूंगा. No.
Sir, one request.
Yes.
Could you speak in English always?
Yes, sure.
I can't understand.
Yes, okay. Sure. Yeah. So, why polymer shows a non-linear behavior? And my next question, do metal show linear behavior always?
Sir, because here the U is more, so we cannot ignore the higher order terms. Maybe
higher order terms comes place in rubber.
So when the U value is high, then what will happen?
non-linearity will come.
Then
U
higher order
and
terms
U.
will come into play. U cube, U to the power 4, U to the... That again depends on to what level that U is increasing. Whether this value is sufficient or this value will come, isn't it? So whenever higher order term comes into play, then here there will be another function of another constant into U square. So whenever there is a U square, will they follow a linear relation?
No.
No. Answer is no. My next question is, do metal always follow? Do metal also completely follow linearity?
No, sir.
How you know?
Anelasticity, sir.
Anelasticity is different. Anelasticity, I'm not coming this thing. Anelasticity is time dependent. You are right. What you said is right. Anelasticity is time dependent behavior, that with time it comes back. So it follows a nonlinear way. And with time, strain also increases. You have given a good answer. But in this context, I am not taking this, because here I am not considering time dependent deformation. Here I am considering instantaneous deformation. Have you heard these two terms under stress strain curve? Have you heard the two terms? Have you heard these two terms? Can you read what I have written?
Yes, sir.
Yes.
Yes. Now you define what is the difference between them.
The proportional limit is totally linear up to linear point. After that.
Yes, proportional limit, you say that stress is directly proportional to strain, right? So what you said is very right. You say linear part. Then what is elastic limit?
After that, there will be some decreasing slope. It will become linear.
So why there is two different term? That is my question. Fundamentally, you think why these two different term?
So
One
actually,
term.
proportional limit is
Yes. Yes.
So proportional limit is up to which Hooke's law is obeyed.
Hey, right. And then
So elastic limit, it's a maximum stress that material can again back to the original shape.
Right. So Hooke's law, I would say, if you consider the generalized Hooke's law, it is always obeyed in elastic region. But if you consider the F equal to Y into U, yes, this part is obeyed up to which point? Up to which point?
Elastic
proportional limit. Up to proportional limit. Then what is happening between proportional limit to elastic limit?
So stress will decrease afterwards if it is further strained. Upper yield strength and lower that.
No, that is, we are not yet at the yield strength. You are absolutely not right. We have not reached the yield level.
So the other higher order terms will come to play when we
absolutely right.
After crossing proportional.
After crossing proportional limit, there is a little bit of non-linearity. There is a little bit of non-linearity. So the question can come whether you will consider this difference. Some textbook, they say that whatever proportional limit, that is elastic limit. But if that is the case, then why there is two name? Why there is two different definition? Because there is a little bit of possibility that in this domain, the U value becomes such that a little bit of U squared term is coming into play. That's why non-linearity. That's why non-linearity. So elastic, there can be two kind of elastic. One is linear elastic. Another is
yes. So Hooke's limit, Hooke's law, we will consider till elastic limit or proportional limit.
Yes.
So Hooke's law.
Now, if you consider Hooke's law, it is up to the proportional limit.
Up to proportional limit.
Up to proportional limit. ठीक है? उसके बाद non-linear elasticity. Elastic is there, but a little bit of non-linearity is coming into play. So as someone rightly said, that Young's modulus is changing with strain at that particular portion. So non-linear elasticity. So by now you understand a curve is not linear doesn't mean that it is not elastic. A curve can be non-linear, but still elasticity can be there. It's not mandatory that a curve has to follow linear behavior to maintain elasticity. So that is the difference between proportional limit and elastic limit. So if someone asks you fundamentally which point should come earlier, proportional limit will come first or elastic limit will come first. If someone asks you to draw a curve and indicate proportional limit and elastic limit.
Proportional limits are first.
Yes, proportional will come first, elastic will come then. Now my next question is, if you have heard another term which is yield point. I am confusing you a little more. Yes.
Sir, how to differentiate those elastic point and proportionality point there in the graph, sir?
Yeah, in the graph you may not be able to distinguish. In the graph you may not be able to distinguish. You must know why there is a difference fundamentally.
Okay, sir.
There is one more question. So if we are considering the higher order terms,
yes, then
why is this graph in elastic limit dipping down? It should go a bit up. Why in the EP region, here in the sigma A graph?
Okay. So that will, yeah, I understand, but that will depend on the values actually, I think, right? Because the coefficients are also coming into play. It's also only that not U square, but the coefficient. It's a good question. Think. I may not be able to give all right answers. Huh? You think. Very good question. Who has asked this question? Kumar Ayush. Think a little bit. Huh? Then let me know. I may not know everything. Okay. You tell. My gut feeling I told, because the constant value is also coming into play. With U square, C is also coming into play. And U value is very small, so it's in a decimal. If you consider decimal, then say U is 0.1, suppose. Then what is U square? U square is not more, but U square is 0.01, right? So the very small values in decimal, if you do square, it will be smaller, even smaller. So you think and let me know, okay? What is yield point? What is yield point? This is my question.
After which elastic deformation.
Tell, what is yield point? Yes.
Plastic deformation.
After which plastic deformation happens. Very good answer. Okay, let me take that answer. Then what is elastic limit?
Elastic limit is
up to which elasticity is valid, right? Then just after elastic limit, what is happening? It's a no man's land. If someone asks you to draw elastic limit and yield point, how we will draw?
Yield point will be after the elastic limit, because we take that 0.2%.
Right. So what is your name? You were right. What you were saying? What is your name?
Sampath Barik.
Sampath Barik. Very good. Very right, Sampath. You now tell that.
Sir.
Yes.
Sir, I have a question.
Yes.
Sir, can we really distinguish between when the elastic limit ends and the plastic limit starts?
Yes, you can distinguish. What is elastic limit? First you tell. Distinguishing will come afterwards.
Sir,
who has asked this question? On this, I am asking you. What is the fundamental definition of elastic limit? You tell.
Sir, till which the
elasticity is valid. So just if you cross one minute step beyond that limit, what is happening inside the material?
So plastic deformation starts.
Aye, then what, Kumar? Are you said that at yield point plastic deformation starts?
Yes, sir.
Actually, in yield point, permanent strain reaches 0.2.
So
before yield point,
we can
also,
think.
So
we can think in different way also. There's a proportional limit that it will be directly proportional. It will regain its shape, and in between the E and
after
T,
proportional limit
elastic-
also, listen, after
certain
proportional
amount of
limit also it will regain its shape. After proportional, even if it is non-linear elastic, then also it will regain its shape. As I said, no time, no, it is not a time dependent function. I am telling you, not time. Immediately it can come back. Here I am not considering time. Even in instant deformation, higher order terms are coming into play. So ideally from here again, it will come back to 0. So what is elastic limit?
Sir, at yield point, it acquires the sufficient amount of activation energy and breaks the bond and rejoin.
Break? Absolutely not right. You have said wrong. Break the bond to do fracture. No.
No, sir.
No. So you are saying that break the bond and do slip? Huh?
Sir, elastic limit is the
Yes, sir.
break.
Yes, sir.
Yes. Okay. So again, that means you are saying the same thing, that at yield point plastic deformation starts. Because whenever there is a slip, there is a plastic deformation start.
But when unload, it retains its position.
Try to think, what I am saying, try to think in a logical way. Don't give ulta-pulta answer. Think in a logical way.
But why you have written in the non-linear elastic, sir? Sir, there should be a transitional partner between this proportional, when we go from elastic to non-elastic part. That can be taken as
I am not saying non-elastic part. That's why I'm asking up to elastic limit. Here I am writing E. Here I am writing E, elastic limit. Here I am writing P, proportional limit. And between proportional and elastic, I am writing non-linear elastic. It is elastic. If you release the load, it will come back to 0.
So that will also be taken. That will be instantaneously.
Instantaneously.
No, instantaneously. I am asking that from E to 0, it will occur instantaneously. No time dependent.
Yes.
No time dependent.
No time dependence. No time dependence. Time dependence, I am not coming here. Again and again, I am telling instantaneously. What is the definition of, so what misconception we have so far? There is a misconception I am trying to indicate. What is that misconception? The misconception is, it is wrong to say plastic deformation starts at yield point. It's wrong. If so far you know that, what you have known so far is wrong. Plastic deformation does not start at yield point. Try to put this information in mind, the definition in your mind. So what I said, repeat, please repeat. One or two of you, please repeat.
So that
plastic deformation doesn't start in yield point.
Absolutely right. So where does it start?
After the elastic limit.
After the elastic limit. That's why its name is elastic limit. And immediately after that elastic limit, plastic deformation starts. And how the plastic deformation starts? what will happen? That you will say that a plastic deformation has started.
A dislocation started
A
moving.
dislocation will move and a slip step will produce.
Yes.
The first slip step will produce. That is the first permanent deformation, right? If you have a specimen, if there is a slip step, you can produce one slip step, small. There is a slight increase in length. That is the plastic deformation starts. Right? Now if I ask you, how much will be the increase in length because of that step formation? You give me a value. Huh? You give me a value. If one step forms, typically how much is the permanent deformation that is happening?
1 Bajaj factor.
How much is that? How much is that?
A0.
Give me a number. Give me a number. 4 angstrom. 4 angstrom, let us say. 4 angstrom. Okay. So this step is basically 3 or 4 angstrom. So because of this increase in height, let us assume even if the same. So let us write it as 3 angstrom. What is the size of a tensile specimen? What is the gauge length of a tensile specimen? Typical gauge length.
25 mm, sir.
A very good answer. Say, I take your answer, boss. You very right. Small specimen, 25 mm gauge length on which I am measuring. So over a length of 25 mm, how much will be the increase in length because of one step formation?
4 angstrom.
4 angstrom.
4 angstrom, suppose. So will you be able to see this effect on the stress strain curve? Huh?
No, sir.
No. So you will not identify that elastic limit. You will not even identify the linear and nonlinear elasticity. Like that, you will not even identify that first step has formed inside a 25 mm specimen. When it happened, you never know. So when you will identify, because you need to identify to know where the plastic deformation starts. To tell your friend, to tell the design person when plastic deformation start. You have to tell a realistic value, na? So you keep continuing with your journey.
Continuously deforming.
You keep continuing your journey till you please note down what I am saying. Please note down. Till a small but detectable amount of plastic deformation you see. Small but detectable. It need not be more, but detectable. Small and detectable. Because before that it is undetectable. So you will not be able to tell if someone asks at what stress plastic deformation actually starts. You cannot give any idea because you don't know. From the curve you will not see.
So
what you
if the technology improves, then our definition will keep.
Yeah. That I take. But why these concepts? These concepts are long back, right? And these are engineering concepts. That's why yield strength, there is no as such yield strength inside a material. Definition is small but undetectable. And we define the yield strength in our own way.
Excuse me, sir.
Yes.
So can we say this to mild steel also? There is a yield point phenomena.
There is a yield point phenomena. True. There is a yield point phenomena. Why we consider that yield point phenomena? as yield strength? Because we see that phenomena. So from that phenomena, we know that dislocation movement has started. Before that, we don't know. So because in steel that phenomena happens at the very initial stage of deformation, that's why yield point phenomena values we consider at yield strength. But in aluminium, what you will do, my friend? In steel, there is a benefit, there is an easy that there is an yield point phenomena at the very initial stage. You know that when the deformation starts, yield point phenomena, and that's why you strike that yield point phenomena is yield strength. Because yield strength is your engineering concept. If it is a continuous curve, what you will do?
We have to do yield offset.
Then you have to take an offset method. That you take a small amount of permanent strain, draw a curve parallel to your elastic line. Where it cuts, that is your yield strength. And how much strain offset generally we take? 0.1 or 0.2%. 0.1 or 0.2%. I'm ending very quickly. Don't be restless. Time is up. I'm just quickly ending. So if I take 0.2% permanent strain, my gauge length is 25 millimeter. So how much displacement is needed? How much permanent displacement is needed? You tell. Suppose I take 0.2%, that means strain of 0.002 and engineering strain of 0.002 over the gauge length of 25 millimeter to detect that point, to detect the curvature in the curve, that the curve is not linear and it's moving because of plastic deformation. For that, how much displacement is needed?
50 microns, sir.
Very good. Say 50 micrometer. Now, next question is, to achieve 50 micrometer permanent deformation, how many dislocations you need to move inside that structure?
One lakh 25,000, sir.
You say in the form of 10 to the power?
So 10:5.
10:5 to 10:6, right? 10:5 to 10:6 over this range. My God. To define the engineering concept of plastic deformation, which is small and detectable plastic deformation. Detectable. You please write down. Small and detectable. This question will come in your exam. Table.
So I also have
small
a question.
And detectable.
So what
for
is the
that,
difference?
how many
So what is the difference between? Yeah. What is the difference between plastic deformation and yielding? Said yield strength you told.
There is no difference in plastic deformation and yielding.
So you told that plastic, this deformation doesn't start at the yield strength. You stored that from elastic, and the yield strength also we are defining.
Exactly.
So
Exactly. Plastic deformation starts at yield strength, but you cannot detect that point, na? Can you detect the elastic limit from an engineering concept? Suppose 200 years back, people used to do tensile testing. People made so many bridge, sword, all these things. Tank, 500 years back, 1000 years back, that time. How will you detect elastic limit?
So can I say also that yielding will also start from E point elastic limit? Because
yielding is not the right. Yielding is not the right. Don't use the word yielding. Yielding is Don't use these words. Okay, sometimes some words are confusing.